Hey guys, so today we're going to be talking about section 5.2, which is systems of linear equations in three variables. So section 5.1 was all about systems of equations in two variables, and we learned how to do that with the addition method and with the substitution method. And so today we're going to talk about how it works when there's three variables instead of just two. So instead of x and y, you're going to have x, y, and z. So here's the good news. It works the exact same way. The only thing that's different is obviously, you have a z variable now instead of just an x and a y. And you also only really deal with the addition method in order to solve these. We don't really have a substitution method because that doesn't help us much, because the substitution method with two variables allowed us to eliminate one of the variables by substituting it in. But when you have three variables, it doesn't work that way. So you're only going to do the addition method. It is a little bit longer because there is a couple extra steps that you have to do, but it's the exact same process. So that's the good thing. You're not learning a new process, you're just learning how to do it on more complicated equations. So let's see, probably right there is the best. So before we actually start solving the systems of equations, just like in 5.2, we had to determine if an ordered pair was a solution. And in this case, we're going to determine if an ordered triple is a solution. So it's the exact same thing. You're going to plug in this triple into each of the equations and make sure you get a true statement out. Yes, you do have to check every equation, because if not, then you don't know if it's a solution for all three of them. And instead of an x, y coordinate, you have an x, y, z coordinate. So anywhere there's an x, I'll plug in a -1. Anywhere there's a y, I'll plug in 2. And anywhere there's a z, I'll plug in a -2. I'm going to do that for every single equation. So I'm just going to look at this top equation. And it says x, so that's -1, plus 2 times my y value, which is 2, minus 3 times my z value, which is -2, equals 9. It's -1 plus 4 plus 6 equals 9. -1 plus 10 equals 9. I get 9 equals 9, so that's good. So it works on the first equation. Let's check the second one. I have 2 times our x, which is -1, minus our y, which is 2, plus 2 times our z, which is -2. And all of that needs to equal -8. -2 minus 2 minus 4 equals -8. -8 equals -8. It works on our second equation, so that's good. We just have one more to check. So it says we have a -x plus 3 times our y minus 4 times our z equals 15. Negative times negative is a positive. 3 times 2 is 6. -4 times -2 is a positive 8. 8, or 6 and 8 makes 14, 15. So we have 15 equals 15, check. So since it worked in all three of our equations, then we know that this triple is a solution to that equation. If at any point we would have gotten something that was untrue, we would have gotten 9 equals -8 or anything like that, we would have known then that it's not a solution. Again, this works exactly like it did in 5.2, only instead of an ordered pair, we have an ordered triple. And like I said, we don't have any other method with doing a system of equations in three variables except the addition method. So that's kind of nice. So we have the addition method and we have our system of equations. If you have a hard time reading what I'm writing here, you can always pull up my notes. I work literally straight through them so you could see it a little closer and understand a little better. Unfortunately, I can't get you any closer just the way the room's set up. But there's our system of equations. We have 5x minus 2y minus 4z equals 3. 3x plus 3y plus 2z equals -3. And a -2x plus 5y plus 3z equals 3. And like I said, this works exactly the way that it would with two variables, only now we have three. And so we're going to have to do the methods more than once, because with two variables, with the addition method, as soon as we added the two equations, one of our variables would drop away. And that's what's going to happen when we do it with three variables. However, that will only get rid of one of the variables, and then we're going to be left with two equations with two unknowns, so we have to do it again. So what I do is at the very beginning, I label my equations 1, 2, and 3, because you're going to have a lot of equations popping up, and this is the easiest way I found to keep track of all of my equations. And then I'm going to just look at my first two. I'm going to look at 5x minus 2y minus 4z equals 3. And then I'm also going to look at my second equation, which is 3x plus 3y plus 2z equals a negative 3. And then remember, the whole point of doing the addition method is to get rid of one of our variables. And if we can't just do that, then we have to multiply one or both of the equations by a constant in order to eliminate one of the variables. So I'm going to look at all of my variables and ask which one is the easiest to eliminate at this point. Well, we have 5x and 3x. Those aren't going to just add away, and I have to multiply both equations, so that's probably not it. I have 2 and 3 for my y's. Again, those aren't going to add and go away, and I probably have to multiply both equations to get it to eliminate. Here I have negative 4z and a positive 2z. Well, if I multiplied the 2z by 2 and added it to the negative 4z, then my z's would go away. So I'm going to do that. I'm going to multiply this bottom equation by 2 so that I can add them together and get them to go away. So equation 1 does not change. We have 5x minus 2y minus 4z equals 3. And then equation 2, I'm multiplying everything by 2, which will give me 6x plus 6y plus 4z equals a negative 6. That way I can add them up. I'll get 11x plus 4y. My z's are going away, which was the whole point, equals a minus 3. Now at this point, I'm going to label this equation, equation number 4. That way I don't lose track of it. Because equation number 4 is different. It only has x's and y's in it. It doesn't have a z. So I want to make sure I keep that one straight. Okay, so that was with equation 1 and 2. Now I'm going to look at equations 2 and 3. So equation 2, going back to the original, was 3x plus 3y plus 2z equals a negative 3. Equation 3 was negative 2x plus 5y plus 3z equals 3. Now, at this time, though, I don't have a choice about which variable I need to eliminate, because I need to eliminate the same variable that I eliminated the first time. And what was that? Well, we got rid of our z's. So I need to look at these two equations. I have a 2z and a 3z, and I need to think, what do I need to do to get them to go away? Well, I need to multiply one of them. I need to multiply the top one by 3 and the bottom one by 2. But since they're both positive, I need to multiply one of them by a negative in order for them to add together to eliminate. It doesn't matter which one. I did a minus 3. That was just my choice. If you did a minus 2 instead, it would work as well. So I'm changing my number 2 equation again. So I'm taking everything in the number 2 equation, multiplying by negative 3. So I have a negative 9x minus 9y minus 6z equals, and then negative 3 times negative 3 will give me a positive 9. For my third equation, I'm multiplying everything by 2. So I get a minus 4x plus 10y plus 6z equals 6. Now I'm ready to add them together. I get a minus 13x Negative 9y plus 10y will give me a positive 1y. My z's go away. That was the point. Then I have 9 plus 6 is 15. And this will be equation number 5. So there's lots of equations that you have to keep track of. That is the added thing with a triple. But now if you look, my equation 5 only has x's and y's. My equation 4 only had x's and y's. So those are going to be the next two that I want to try and eliminate something from. Okay, so I'm going to write 4 right over here so that we can have them under each other to compare them to see if they're ready to add. So if I add my 5 with my 4, do my x's go away? No. Do my y's go away? No. So I need to multiply one of them by something in order to get rid of one of my variables. Well, my x's are negative 13 and 11. Well, those are not multiplied. Like, you can't multiply those easily because they're both primes. But then I have 1y and 4y. And they're both positive. So if I multiply equation 5 by a negative 4, then that's going to allow me to eliminate out my y's. So instead of writing equation 4 again, I'm just going to write equation 5 altered underneath it. So I have equation 5 where I'm multiplying everything in it by the negative 4. And that's going to give me 52x minus 4y equals a minus 60. So now I can add them. I get 63x, my y's go away, and I get minus 63. Now I can just solve for my x because it's all isolated all by itself. Divide both sides by 63, and I get x equals negative 1. And right there is the first term of my ordered triple. Sorry, I'm going to move you down because I'm running out of board space. So then what do we do with that? Well, we can plug it back into either equation number 4 or equation number 5 in order to solve out for our y. We don't want to plug it into one of the original equations because the original equations also had the z term. So we just want to take it back up to either equation 4 or 5 and plug it in. It does not matter which one. I plugged it into equation 5, which was negative 13x plus y equals 15. I chose to use this equation instead of the equation 4 because y, it doesn't have a coefficient. And so that's going to make solving it a little simpler. So I have negative 13 times our x value, which was negative 1. That makes that a positive 13. Subtract 13 over, and I get y equals 2. There's the second part of our triple. Now we can go back and pick any of the original 3 equations, equation 1, 2, or 3. It does not matter which one. None of them have z by itself, so I just went ahead and used equation 1, which was 5x minus 2y minus 4z equals 3. Plug in a negative 1 for my x, plug in 2 for my y, and then I'm going to end up solving for my z. Negative 9 minus 4z equals 3. Add the 9 over. Negative 4z equals 12. I'm going to divide both sides by the negative 4, and I get z equals a negative 3. Then I can write my ordered triple of negative 1 to negative 3. Now, it just so happened that we found them in x, y, z form. It doesn't matter who would have found z first or y first or x first. Just make sure that when you write it in x, y, z form. So you have to keep track of those. And I always label my equations with my circled numbers to help me. Some people like to highlight and they make them different colors. whatever helps you, because there is a lot of equations. You will end up with 5 equations pretty much every time you work one of these. And so this will just help you to keep track of them. The steps are the same as with 2 variables. You just have to do them twice, because you have to do the 2 equations to get down to the equation with just 2 variables. Then it's like starting from chapter 5.1, where you have 2 equations with 2 unknowns, and you do that, and then you back substitute and back substitute. We're going to do another one, because I know there's a lot of steps. All right. Let me get as much board space in there as I can. Okay. So example number 2. Again, these are on my notes if you need to pull them up to look at them. We have x plus 4y minus z equals 20. We have 3x plus 2y plus z equals 8. And 2x minus 3y plus 2z equals a negative 16. Once again, I'm going to label them 1, 2, and 3. And I'm also going to look at equation 1 and 2 first. I'm just rewriting the first 2 equations by themselves. And then I look at my variables and I ask which one's the easiest one to eliminate. I have x and 3x, 4 and 2, and negative z and a positive c. Well, right there, if I add, my z's are going to go away. So I'm going to do that and just eliminate my z's again. So I get 4x plus 6y equals 28. And that'll be equation number 4. So that one worked out really nice. So now I'm going to look at equation 2. And equation 3. Once again, this time I don't get to pick and see which one looks the nicest to eliminate. I have to eliminate the z's so that my equation 4 and equation 5 only have x's and y's in them. So I need to just look at my z's. I have a z and a 2z. So if I multiply this top one by a negative 2, then I'll be able to eliminate it. So instead of rewriting 3 again, I'm just going to write the altered 2 below it. So negative 2 times everything in equation 2 would give me a negative 6x minus 4y minus 2z equals a negative 16. Add them together and I get a minus 4x minus 7y. My z's go away, equals a negative 32. And this is equation number 5. So I'm going to write equation number 4 over here so we can look at it. We have 4x plus 6y equals 28. Well, look at your x values. We have a negative 4x and a positive 4x. So these are already ready to add. That makes it nice. So we have a negative 7y and a positive 6y. We have a negative y equals a negative 4. Multiply both sides by negative 1, we get y equals 4. So sometimes you don't have to do quite so much of the math by multiplying one or more equations. Sometimes our stuff is ready to just go away. And that makes it nice and we can simplify easier. Notice this time we found our y value first. Totally fine. I'm going to plug that into one of the either equation 4 or equation 5. It doesn't matter which one. It looks like on my notes I went back to equation 5. So I'm going to do that, which is negative 4x minus 7y equals negative 32. So anywhere there's a y, I'm going to write 4. Minus 28 equals minus 32. Negative 4x, I'm going to add that 28 over, which will give me a 4. It's negative though. So divide both sides by negative 4 and I get x equals 1. There's my second part of my ordered triple. Now I plug both that x and that y value into one of the originals. I'm going to plug it into the second one because then z is positive and it's by itself. And my notes on there, I plugged it into the first one, but I just noticed that z is positive in the second one, so I'm going to plug it in there. So I have 3x plus 2y plus z equals 8. And not all of that is on there, so I'm going to shift. There you go. Anywhere there's an x, I plug in 1. Anywhere there's a y, I'm plugging in 4. I get 3 plus 8 plus z equals 8. So I have 11 plus z equals 8. Subtract 11 over, I get z equals minus 3. Now to write my ordered triple, I write my x value first, which is 1. I write my y value next, which is 4, and then negative 3. And there is my ordered triple, which is a solution for the system of equations. Sorry, I don't know where to stand without blocking. There's one other situation that you may see, and I call it the missing term. It's not like a special way of doing it. It just basically, they've eliminated one of the variables from one of the equations already at the very beginning. And so that is the variable you want to eliminate from the others. And so I made it really noticeable by leaving a big gap in this system of equations. We have x plus z equals 8. We have x plus y plus 2z equals 17, and x plus 2y plus z equals 16. So again, I'm going to label these 1, 2, 3. And I call this a missing term because in our first equation, we don't have a y term. That's totally okay. You don't always have to have the same terms. But what that means is when I look at equations 2 and 3, I want to eliminate my y term so that I end up with my equation 4 being in terms of only x's and z's. So in this case, I'm not going to have an equation 5. I'm just going to have an equation 4. So if I'm just looking right here at equations 2 and 3, and I have to eliminate my y's, that means I have a y and a 2y. So I need to multiply equation 2 by a negative 2 in order to eliminate that. So if I multiply everything by negative 2, I get a minus 2x minus 2y minus 4z equals a minus 34. Now I can add them. I get a negative x, my y's go away, and I get a minus 3z equals a negative 18, and that's equation number 4. And it's in terms of x's and z's, just like my equation 1 was x plus z equals 8. Now here's the nice thing. This is already ready to simplify out again because I have a negative x and a positive x, so those will go away. Negative 3z plus z will be a minus 2z. Negative 18 plus 8 would be a negative 10. So I get z equals 5. So I divided both sides by negative 2. Now I'm going to plug that back into my original equation, equation 1, because equation 1 was x plus z equals 8. Doesn't really get much simpler than that. So I'm going to plug in a 5 for my z. So I get x plus 5 equals 8. X equals 3. So now I have my x and my z. So I'm going to plug it into equation 2, because equation 2, the y is all by itself. I have x plus y plus 2z equals 17. My x we just found was a 3, y, and then my z was a positive 5. 3 plus y plus 10 equals 17. 13 plus y equals 17. Subtract 13 from both sides, and I get y equals 4. So my ordered triple this time will be 3, 4, because that's my x, my y, and my z. So if you're missing one of the variables, that doesn't mean you can't do it. It doesn't even make it more complicated. It actually makes it simpler because we have less equations to deal with, because basically we already know which variable we're going to eliminate from the other two equations, and thus we have eliminated one of our steps. So don't let that scare you or intimidate you. And that is actually the end of 5.2, systems of equations.